Hi and welcome back again. In this video you will learn all about quadratic forms. We call a function q a quadratic form on Rn if it is the weighted sum of terms that are all either squares of a variable or the product of two different variables. Quadratic forms occur often in many areas of science and engineering, since many geometrical objects can be described in terms of quadratic forms. For example, by considering equations where we set a quadratic form equal to a constant, meaning so-called level curves of the quadratic form, we can consider all sorts of well-known geometrical objects such as an ellipse, a hyperbola, or two lines going through the origin. In fact, each of these particular examples are one of the so-called conic sections, which you obtain by intersecting a double cone with a plane. These conic sections occur often in nature, for example when considering planetary orbits, which are elliptic. In addition, the shape of objects such as reflector dishes can be described as level curves of quadratic forms. But you are following a course on linear algebra, so why would you care about quadratic forms? Well, you can easily construct quadratic forms by considering a square matrix A and letting Q of x be defined as x transpose AX. For instance, if A is the n times n identity matrix, the corresponding quadratic form is the square of the norm. So let's consider a slightly less trivial example. If we work out x transpose AX for this particular matrix A, we obtain the following quadratic form. The terms which are a product of two different variables are called the cross terms. So let's see where each of these entries of the matrix ended up. First, we note that the diagonal entries come back as the coefficients of the corresponding square terms. In addition, the 1, 3 and 3, 1 entries add together to the coefficient of the cross term x1, x3. And similarly the 2, 3 and 3, 2 entries to the coefficient of the x2, x3 term. Finally, there is no x1, x2 term since both the 1, 2 and the 2, 1 entries of the matrix are 0. So for any square matrix we obtain exactly one quadratic form. Let's see if we can reverse this process. Consider the following quadratic form. To make the computation more clear, we also write down the missing x1, x3 term. In order to write q of x as x transpose AX, we note that the coefficients of the squares need to come back as the diagonal entries of A. Here we have no choice. Now let's have a look at the cross terms. The 1, 2 and 2, 1 entries should add up to minus 6. The 2, 3 and 3, 2 entries to 8 and the 1, 3 and 3, 1 entries to 0. But that leaves us with several different options, of which we have shown two. However, only one of these choices leads to a symmetric matrix. Since you know that symmetric matrices have some very useful diagonalization properties, we will always describe Q using a symmetric matrix. Indeed, the preceding considerations lead to the following theorem. For any quadratic form Q on Rn, there exists a unique symmetric matrix A such that Q of x is x transpose AX for every vector x in Rn. Since quadratic forms are also functions with the real numbers as codomain, we can take a look at their graphs. Here you see a few examples. For each of these examples, determining the shape of the graph is relatively straightforward, since we can simply determine the behavior in the x1 and x2 directions and derive the general shape from that. But how would you do that if the quadratic form has cross terms, such as this particular quadratic form? In that case, a well-chosen change of coordinates turns out to be of much help. Indeed, we consider a quadratic form q of x is x transpose AX for a symmetric n times n matrix A. Then there exists an orthogonal matrix P such that the change of variables x is py transforms Q into a quadratic form with no cross terms. This result is known as the principal axis theorem, and the lines generated by the columns of P are called the principal axis of Q. We will prove this result by algorithmically constructing this matrix P. Of course, you know that what makes a symmetric matrix special is that it admits an orthogonal diagonalization. So if we write A as PDP transpose with P orthogonal and D diagonal, we write B for the orthonormal basis consisting of the columns of P. Then we define the new variable y as x in terms of this basis, which means that we have y is P transpose times x. Since P is orthogonal, we get x back by computing P times y. Then we can write Q of x in terms of the new variable y as y transpose dy. Please pause the video to check these calculations. Since D is diagonal with the eigenvalues of A as diagonal entries, we can work out y transpose dy and find the quadratic form without cross terms. So let's consider the example from before and let's see how we can use the principal axis theorem to draw the graph. From the quadratic form we can directly determine the corresponding matrix A. This matrix has eigenvalues 5 and minus 10 and we find a corresponding orthonormal basis of eigenvectors. So we obtain the following transformation matrix P, which has these eigenvectors as columns. Then, in terms of the new variable y is P transpose x, we find that the transformed quadratic form is given by 5y1 squared minus 10y2 squared, which does not have any cross terms. This can easily be drawn in the y1, y2 coordinate axis. And if we include the x1, x2 coordinate axis, we see that we have drawn the graph of the quadratic form. Here you see both the graph and the corresponding contour plot. In order to draw the graph, it is therefore necessary to first draw these principal axes in the x1, x2 coordinate system. So if we want to draw the y1 axis, for instance, we should find out for which vectors x the y2 coordinate is 0. This means that we must compute p times the vector y1, 0. And we see that the y1 axis is a line through the vector 2 over square root of 5, 1 over square root of 5. Note that the principal axes are orthogonal, since P is an orthogonal transformation. Finally, we can also use this to easily draw level curves of this quadratic form. In the version without cross terms, we can directly see that the level curve Q is 0 corresponds to 2 lines through the origin. We can draw these lines in the y1, y2 coordinate system, and with that we have immediately drawn them in the corresponding x1, x2 coordinate system. That's it for now. Don't forget to practice the material and see you next time.